In previous lectures, we introduced positional notations and the unsigned binary representation of numbers. In this lecture, we introduce a new binary representation that allows us to represent negative numbers. This new representation is called 2's complement representation. If we want to interpret a 2's complement represented number, we can determine its value using techniques that we learned when we discussed positional notations. Given a specific number of bits, the rightmost bit has a weight of 1, the second rightmost bit has a weight of 2, and so forth, just like unsigned binary representation. The most significant bit has the magnitude that we might expect, but it has a negative weight. So let's consider this 4-bit number. In unsigned binary, this number is 11. But in 4-bit 2's complement representation, this number is negative 8 because of the negative weight for the most significant bit, plus 2, plus 1, or negative 5. The convenient thing about 2's complement notation is that we can add negative and positive numbers with the same algorithm that we use for unsigned binary. So let's add the 4-bit 2's complement representations of positive 5 and negative 5. Ideally, we should find that the normal binary addition algorithm will yield an answer of 0. So 1 plus 1 is 0, and we carry the 1. 1 plus 1 is 0, we carry the 1, and so forth. We cannot store this final carryout of 1, so the computer will store the 4-bit number 0. So it works! So now that we know that we can add positive and negative numbers, we can use this new tool to subtract 2's complement represented numbers. As you know, when we subtract one number from another number, we are actually adding a number that has the same magnitude but opposite sign. So if I want to subtract 3 from 6, I really want to add negative 3 to 6. So how do I convert a positive number into a negative number? I'm glad you asked. Fortunately, 2's complement represented numbers have a convenient algorithm for changing them from positive numbers into negative numbers, and vice versa. Simply, you complement all the bits, change 1's to 0's and 0's to 1's, and then add 1. Finally, because 2's complement representation is constrained by the fixed number of bits used by the computer, we must make sure that the architecture can perform the calculations that we want to perform. An n-bit 2's complement representation encodes a range of negative and positive numbers. For 4-bit 2's complement representation, the representation encodes 16 numbers, from negative 8 to positive 7. Let's check out what happens when we add 5 plus 5. Notice how the most significant bit in the 4-bit number is 1, and indicates that the sum is a negative number. By adding these two positive numbers together, the magnitude of the sum, which was supposed to be 10, exceeded the limits of the representation, which was 7, and produced an error. Similarly, if we add negative 5 plus negative 5, the magnitude of the sum will exceed the lower limits of the representations. Consequently, it will represent the sum as a positive number, which is also an error. This problem is called overflow. More formally, overflow is an error where the magnitude of the sum of an addition operation is greater than what we can represent with the representation. As we just saw, when the magnitude of an addition operation in 2's complement representation was too great, the positive number was wrongfully interpreted as a negative number, and similarly for negative numbers being represented as positive numbers. In the same way, for unsigned binary addition, we can have overflow when the magnitude of the addition exceeds the representation limits. When we add 10 plus 12 in 4-bit unsigned binary, the sum is 22, which is greater than the representation limit of 15. Consequently, the overflow causes the computer to display the sum as 6 rather than 22. To recap, we discussed how to interpret 2's complement represented numbers, how to change the sign of a 2's complement represented number from positive to negative and vice versa, and how to perform subtraction with 2's complement representation, and also the problem of overflow.